Where is the p block in the periodic table? We are referring to columns 13 through 18 on the right-hand side of the table. Elements in the p block have their outermost or valence electrons in a p orbital. As you recall, there are 3 p orbitals in a p sublevel, and each orbital can hold a maximum of 2 electrons. This is why there are 6 columns in the p block. There is a simple relationship between the group number, the number of valence electrons, and the electron configuration. Group 13 has 3 valence electrons, and the electron configuration ends as ns2 np1. As we move across each column to the right, the columns or groups each gain an additional valence electron. The exception, of course, is helium, which has only 2 electrons. Within each of the 6 different families of the p block, there are significant variations in properties. Although all the members of the same family have the same number of valence electrons, their inner cores are different. The variations in the arrangement of the core electrons affect the physical properties, such as atomic and ionic radii, and ionization energies, as well as the chemical properties of the elements in the same family. For p block elements, the maximum oxidation state is equal to the total number of valence electrons. So, as we move from group 13 to group 18, the maximum oxidation state rises from +3 to +8. This is sometimes called the group oxidation state. For the boron, carbon, and nitrogen families, this is the most stable oxidation state for the lighter elements in each group. However, other oxidation states are possible for each group. Often, an oxidation number 2 away from the total number of valence electrons is stable. The stability of oxidation states that are 2 less than the group oxidation state are sometimes attributed to the inert pair effect. As elements get heavier down a column, the oxidation state 2 less than the group oxidation state becomes more stable. This does vary somewhat from group to group. Metalloids and non-metals are found only in the p block of the periodic table. Down a column, the non-metal character of the elements decreases. The heaviest element in each column has the most metallic character of that family of elements. There is a lot of diversity in the properties of p block elements. Since a given family may have metals, metalloids, and non-metals. Metals and non-metals have distinctly different properties. When comparing metals and non-metals, non-metals typically have higher ionization energies than metals. The electronegativities of non-metals are generally higher than that of metals. Therefore, metals readily lose electrons, forming cations. Non-metals typically gain electrons, forming anions. Compounds formed between a metal and a non-metal are essentially ionic in nature. This is due to the large electronegativity difference between the elements. The metal transfers an electron to the non-metal, and the oppositely charged ions that result are strongly attracted to each other. Compounds between 2 non-metals tend to be primarily covalent in character. The small differences in electronegativity result in a sharing of electrons. Oxides of non-metals are either acidic or neutral in nature. Acidic oxides, such as nitrogen dioxide, will form acids when dissolved in water. metal oxides are usually basic. For example, when magnesium oxide is dissolved in water, hydroxide ions will form. Let's focus our attention on the group 13 elements. The members of the boron family include boron, aluminium, gallium, indium, and thallium. The elements in group 13 exhibit a wide variety of properties. For example, boron trioxide is an acidic oxide. Aluminium oxide and gallium oxide are amphoteric. They can act as both acids and bases. The oxides of indium and thallium are basic. The first member of each family in the P block, that would be boron, carbon, nitrogen, oxygen, fluorine, and helium, have the smallest atomic radius in their respective families. Each of these exhibits some anomalous behavior as a result. For example, the elements in period 2 have a maximum covalence of 4. They never exceed 8 electrons because they can only use their 2s and 2p orbitals in bonding. For example, boron can form the complex ion Bf4-. The elements in period 3 and below can achieve expanded octets. Since these elements have unused d orbitals, they can have more than 8 electrons. Therefore, we observe the hexafluoroaluminate ion. We often observe that the first member in each group in the P block can form multiple bonds to itself and other elements in period 2. For example, carbon can form multiple bonds with itself as well as with nitrogen. These multiple bonds involve sideways overlapping or pi bonding of p orbitals. P block elements in period 3 and below can use d orbitals to create pi bonds. As a result, the elements in period 3 and below can achieve a higher coordination number than the first element in the group. The elements in group 13 will be the focus for the rest of this module. Boron is a fairly rare element. Less than 0.0001% of the Earth's crust by mass. This typical non-metallic element is found as a hard, black solid in its pure form. A photograph of boron powder is shown here. In addition to boron powder, boron occurs in several other allotropes, including crystalline boron and alpha boron. Only 2 isotopes of boron are found in nature. Almost 19% of boron atoms are found as boron-10, with 5 protons and 5 neutrons. Boron-11, which has 5 protons and 6 neutrons, is the most abundant isotope. In nature, boron is most frequently found in 3 compounds: orthoboric acid, kernite, and borax. In India, borax is found in the Puga Valley in Ladakh and the Sambar Lake region of Rajasthan. Aluminium is a metal, although it has many chemical similarities with boron. It is the third most abundant element and the most abundant metal in the Earth's crust, contributing 8.3% by mass. Important minerals of aluminium include bauxite, cryolite, and mica. the electron configurations of the group 13 elements all end as ns2, np1. For example, consider the electron configurations of boron and aluminium in noble gas notation. They both have 3 valence electrons. However, if we look at the electron configurations of the rest of the family, we see quickly that they are all more complex than for the s-block elements. This complexity affects the chemistry of this group. While boron and aluminium have core configurations identical to the nearest noble gases, as we saw just now, gallium